So there's a pentagon on either side. There's a ladder in the middle of any length you like. And I'm going to think about these things as being summed up with g to the 2l to give some finite coupling function, which I'm just going to call omega. Now, you might be wondering why I would possibly be having a talk on just one specific set of integrals. This seems like a really overly specific technical thing to care about. So in the first part of this talk, I'm just going to give some motivation for why I'm paying attention to these things in the first place, what we might learn from them. I'll then go into a bit where I just talk about what I actually mean by this integral, define my notation, that sort of thing. And then I'll move on to talk about how we can solve this integral for finite coupling. So get the full omega, that's the full sum of all of these things to any loop order. And after that, I'll talk about how we can use that finite coupling expression to derive a space of functions that's much broader than just these things at each loop order. But first of all, let's start with the motivation. Okay. And the key piece of motivation here is that I do the other bootstrap. Okay, so much like the conformal bootstrap you're familiar with, this is also going to involve trying to build up some physical quantity with as little information as possible. Unlike the regular bootstrap, there's a few distinctions. One minor one is that I'm mostly going to care about a specific theory. In this case, planar n equal 4. I'm going to use a lot of different pieces of physical input. In principle, involving some very detailed predictions rather than just sort of going from general principles. But I think the key distinction, and what makes this perhaps a little unusual for this conference, is this approach is perturbative. So the idea with what I'm calling here the other bootstrap, we might more normally call it the polylog bootstrap, the Steinman bootstrap, the hexagon function bootstrap. Anyway, the idea is that we're building up perturbative scattering amplitudes order by order via an ansatz bootstrappy kind of technique. And the reason why this is at all feasible is that the class of functions that can contribute to these things is remarkably nicely constrained. So in particular, for specific helicity configurations, at least for MHV and for NMHV amplitudes, everything in n equal 4 that contributes to them is expected to be, let's see, I'll put this over here, is expected to be multiple polylogarithms of weight 2 times the loop order, where these things, multiple polylogarithms, you may have also heard them referred to as Goncharov polylogarithms, or I guess this group probably wouldn't have referred to them as hyperlogarithms, but whatever. As these other things, there's a lot of different names for them. But the way you can define them is essentially an analogy to the classical polylogarithms. I think that's more disputed. The place where there's good arguments is for the planar case. For non-planar, so far, everything people have found in these sectors still fits, but I don't think there's a clear argument it should keep fitting. Anyway, so for those of you who haven't run into these things before, you might have run into the classical polylogarithms. So then these things end up being defined. So you've got some integral dt over 1 minus t, Li n minus 1 of t. So Lin is defined in terms of Lin minus 1. And then you've got some condition to start. And here it's that Li1 is minus log of 1 minus z. So these things are probably reasonably familiar, or at least you might have run into them at some point. Multiple polylogarithms are a generalization of this, where now it can depend on more variables. So the idea here, this n is what we call the weight of this function, the transcendental weight. Essentially, it's counting powers of pi, or its counting number of integrations. But we can instead define this more general class, and now we have, instead of just a number, what's called a weight vector. So one of these w's for each weight, and these things can in principle depend on any variables of the problem that you'd like. In general, you don't want them to depend on the z, but everything else is fine. And then once you've got things defined in this way, instead of dt over 1 minus t, now you have dt over, I should make sure I get the signs right, yes, dt over t minus w1, and now this function inside the recursion has w2 through wn as its weight vector. So we've just, once again, chopped off the weight at one end, and once again we've got this nice recursive definition, and just like for the LIs, you've got a base case. Here it's g with nothing in the weight vector is just 1, and if you've got all zeros, then it's 1 over n factorial log to the n of z. Okay. So more generally, you can have these dependent on lots of different variables. You can take sums and products of them. So while this definition is sort of nice for building them up order by order, another way to think about them and to think about all functions of this class that I'm thinking of, broadly polylogarithmic functions, is going to be in terms of their derivatives. So everything in this class has the following property, that if you take some derivative of these functions with respect to any variable, what you'll get is a sum of terms, and I'm going to, let's see, yeah, is a sum of terms where we're summing over some rational functions, and here, everything in here is g. This is going to be some g now of one lower weight, d log a rational function s, where these functions s are in some set, which I'm going to refer to as the symbol alphabet. And you can imagine iterating this definition. So each time you've taken a derivative, you've expressed this in terms of these functions and d logs. If you break it up into all the d logs possible, you go all the way down as far as you can take derivatives. That object is called the symbol. So the symbol alphabet is just the letters that appear in this symbol. Yeah, no, so this is exactly the point, is that these functions and any product or sum of these functions is going to obey this property. Right? So I'm just describing these functions in a slightly different way. Instead of using the integral definition, I'm using this definition in terms of derivatives. But I'm just doing this to highlight the idea that we've got these letters. And then in particular, you can sort of think of these functions as defined as having a particular of letters that can show up. It's a little obscured in this form because you can have different variables z here. So probably I should have used something different for here. Yeah, which is potentially confusing. I can call this an F or something. Yeah, sure. Yeah. This F is some sum of G's or some sum of products of G's, but it can depend on all sorts of other variables. And similarly, this Z is not necessarily Z, again, anything else. Okay. But the idea is, once we've got some idea about the appropriate alphabet for, say, an amplitude, we can start building up functions with this property. So, let's see. Maybe write this here. I'll just do this on the other board, actually. So the idea is that you write down an ansatz with a specific alphabet, and there are conjectured correct alphabets for planar n equal 4 that one can use. So one writes down an ansatz for these functions with a specific alphabet. One builds them up order by order, and one applies a few sort of broad physical constraints. So you require these functions to have sensible branch cuts. So this is just saying that whenever you take a branch cut of these things, it should correspond to some Mandelstam vanishing. This is a massless theory. So that's all you're going to see. You're not going to see some massive states. And you impose, more than that, something called the Steinman conditions, where the Steinman conditions are a constraint on adjacent branch cuts, or double discontinuities. So the idea is that if you've got, say, some 6-particle amplitude, and I'm mostly going to be thinking about 6-particle amplitudes here, you could take discontinuities in different ways. So you could take a discontinuity in those momentum invariants, or, say, in these momentum invariants, and you can't draw one Feynman diagram as both of those discontinuities. So if you take those discontinuities together, you need to get 0. And that ends up being the statement of these Steinman conditions. I'm sort of rushing through this because this isn't too central to the talk, but it's just sort of to say we start with some very general physical constraints about what, provided this came out of Feynman diagrams at some point, it has to obey certain analytic properties. So in this case, if it's 2 overlapping cuts, then the result should vanish. Things get a little ambiguous if you've got if you've got 2-particle Mandelstam invariants, but once you've got cuts that are isolating 3 particles, it's reasonably clear in practice what this ends up meaning. These 2 cuts applied sequentially. So to be perhaps a little more explicit, let's say I take discontinuity S123 of discontinuity in S234 of the amplitude, that has to vanish. Well, essentially it's due to this statement about Feynman diagrams. So you can't have one diagram that has both factorizations. And the discontinuity, the branch cut, should correspond to this diagram factorizing in a sensible way. Right? It's taking something on shell, essentially. Okay. So we build an ansatz with this kind of condition, and then we start applying a bunch of different constraints. And once again, I'm going to go through these relatively quickly because it doesn't matter too much for this, but just to illustrate, there's constraints from the dual superconformal. Mm-hmm. Right, essentially, yeah. frequency. We apply collinear vanishing conditions or collinear splitting conditions. We apply information known from the multi-regi limit. We apply information from Pedro and Company's Pentagon approach. So there's in principle a lot of information that we're imposing. But at the end of the day, once you impose enough of these sort of constraints, you get not only a unique answer that fits all these constraints, but you've often over-constrained to the point where if you did have the wrong answer, it would be pretty clear you wouldn't find a solution. So you get to the point where you're at least reasonably confident that you do indeed have the right answer. And by using this kind of method, we've got 6 particle amplitudes now through 7 loops for MHV, 6 loops for NMHV, which, by the way, are people familiar with what MHV and NMHV mean? It might be sort of amplitude-specific jargon, but you've either got 2 minus, all the rest plus, or it's a dual superconformal constraint. I didn't describe it in very much detail because, again, I'm just racing through this particular part. But yeah, this is a constraint that comes from a old paper by Simon Carenfoy, where he figured out that there's an anomaly under the action of Q bar, and so you can use that anomaly to constrain the functions that can show up. And this is, for example, this and everything else in that supercomponent with that combination of velocities. But anyway, we've got these things now through 7 loops in one of these sectors, 6 loops in the other. And I'll put the archive number in case people care. Okay. And this is in general something we're pretty happy about, but at this conference, it feels a little embarrassing because this is still perturbative. And when you're invited to a conference on non-perturbative methods, you start feeling like, well, okay, even if this is to 6 or 7 loops, it's still not actually the full finite coupling expression for anything. And so we start thinking about what it would actually take to do this sort of song and dance for finite coupling. Now, there were sort of some keys to this story. It was key that we knew the type of functions that contributed. And it was key that we had some detailed information about what kinds of things constrain them. Now, a lot of this detailed information actually is finite coupling. The Pentagon OP approach is a particular example. But many of these things aren't just perturbative statements. But the basis of functions, that's the tricky part. It's not immediately clear what sort of functions should actually contribute to a full non-perturbative n equal 4 amplitude. So that's essentially the key question that was on our minds when we started looking at these integrals. What functions work for finite coupling? Okay. And that's where this guy omega comes in. So let me start out defining this function omega. Okay. Now, one thing that's nice about omega is that it is the type of function that you might want. So it is dual conformal invariant. This is, again, not something I defined in a lot of detail, but it's maybe more familiar to people here, since people here have mostly worked with n equal 4 at some point. So this is the statement that you can think about this either in position space or in momentum space, and in position space, it corresponds to a Wilson loop, to a polygonal Wilson loop, which I was not actually planning to draw a picture for this, but I probably should. So the idea is you get some polygonal Wilson loop where now the corners are defined by these dual variables. You get the same expression in both spaces, so you need to have conformal invariants, both these coordinates as momenta and thinking of them as positions. So this omega integral is indeed invariant under this symmetry. Mm-hmm. Yes, so, well, okay. So parts, I should be more specific about this. Yeah, so no, but in that case, that was the superconformal symmetry. So I think just the strict dual conformal symmetry, again, it's also anomalous for the full amplitude, which is why you get higher divergences and the like, but this particular function is going to be invariant under that symmetry. Yes, exactly, because it's finite. Yeah. Yeah, so that's actually perhaps a more relevant point. This integral is indeed finite, but more generally, it satisfies most of those conditions. It has sensible branch cuts because it's a Feynman diagram. It has these Steinman conditions because, again, it's a Feynman diagram, and there's an example of it at any loop order. And in particular, we do know that this thing contributes to the amplitude at every loop order. That is, you can write down the amplitude in some local basis of integrals, and you know that this is some element of that basis at any loop order. There may be many other things. It's no reason to think it's a particular dominant piece of the amplitude, but it's there. Okay. Now, this thing does have numerators, so... Yes. Yes, that is very true. But at any given order, this is going to be there. Okay, so let's see. With this. Yes. So I should be more specific about my notation here. The solid lines are actually propagators. The dashed lines are not. They are numerators. So this thing has specific numerators, which are chosen to make this integral DCI and infrared finite. And in particular, the numerators are going to be of the form L minus L star squared, where L star solves a particular cut condition. So, in particular, if you put this, and this on shell, so if you put sort of all the legs of this pentagon or all the propagators of this pentagon except the one bordering the ladder on shell, then this L star is a solution to that cut. So that L star, if you plug it in, each of those propagators vanishes. Okay. Now, I should be also a little more specific that there are, in fact, two different solutions to this condition for each pentagon. So in principle, then, you have four different options. You can mix and match these things. In practice, most of them are related by parity, and what you actually get are just two solutions. So there's an omega, and I'll just put it over here to remind you it exists. There's also something that I'm going to call omega tilde. So essentially, omega uses the same matching solutions on either side. Omega tilde will use different choices on each side. So omega will have a symmetry that omega tilde does not. Okay. And yes, I already mentioned that these contribute to the amplitude at each order. But more usefully for our purposes and what got us thinking about them is that they are known to obey a differential equation. So this was figured out by Drummond, Hen, and Trinka. And I'm going to start out by writing the differential equation in momentum twisters. I know this is not familiar to everyone. It's going to be in a more understandable form in a bit, but I'll start writing it in this form. So I'm representing the L-loop coefficient of this omega sum as omega superscript L. And what this differential equation does is it relates omega at L loops to omega at L minus 1 loops. So what it's doing, and this is essentially how it was derived, is it's just removing a box from the middle of this diagram. So it just slurps up some box out of that ladder, corrects the numerator so it's still got the right numerator, and continues on, so you get omega at one lower loop order. So this is a second order differential equation, which should make sense given what I've said here. This weight, this number of integrations, is 2 times the loop order. So a second order differential equation will indeed decrease the loop order twice. Okay. So we have this equation. As I mentioned, it perhaps looks a little weird in this form, but I can write it in a slightly nicer form. Let's see. Do I want to put this here or somewhere else? Okay. Let's just do it on this one. So in particular, the key here is picking variables that actually highlight some of the symmetries of this particular integral. So omega is just this thing. Omega L is the L loop coefficient of this thing. So the z's are in momentum twister space, which I know I didn't define in any respect. As I said, I'm about to write this in a form which is a little cleaner. But let's see. I'm trying to think if there's an intuitive way to describe these things. But I think they are essentially in the X space, but they're a different way of representing the X space so that you trivialize some of the conditions. But okay, but so if you sort of look at this thing in the dual space, you can use conformal invariants to make your problem a little nicer. In particular, you've got this x1 and x4, and these things kind of bracket your integral. So you can think about this integral as having symmetries around the axis x1 to x4. And what you can do in particular is you can set, say, x1 to 0, x4 to infinity. So conformal invariance lets you do that. And then once you've done that, you have the symmetries that preserve that. So you have symmetries preserving the positions of x1, x4, now that you've sent them off. And in particular, what you still have are an SO4 of rotations around this axis and a GL1 of rescalings. And you can break down this SO4, if you like, into an SU2 left and an SU2 right. So this thing is really much more nicely expressed if you use variables that actually behave nicely under this breakdown. So what I'm going to do is I'm going to define an, let's see, I just need to remember which one goes to which, an x, which transforms only under the SU2 left, a y, which transforms only under the SU2 right, and a z, which transforms only, make it clear it's a lowercase z, only under the GL1. Okay. And in these variables, this differential equation turns out to be quite nice and tidy. So what we have is 1 minus y over y times y dy squared minus z dz squared minus g squared. Now, I'm writing this in a slightly different way because that equation was written just as a relation between loop orders. What I'm going to do is now write this with an explicit g squared. So if you expand this equation in G, what you'll get is just the equation above. And if you change the variables back. But now the idea is you can think of this not merely as a relation between perturbative loop orders, but as a finite coupling statement, right? So now we've just got to manifest G squared, and we're just going to treat it as some variable in our problem. And in addition to this, you'll notice this just has y in it. There is also this with y exchanged with x. So this particular integral is invariant under exchanging y and x. Yes. Yes. I mean, essentially, this is there are 3 cross ratios we can write down, so this is just a choice of 3 cross ratios that make the problem nicer. Okay. And with this, let's see where I want to put this. I guess I can put this over here. Okay. You can probably ignore that guy for the moment. What we're going to do now is we're going to talk about solving omega at finite coupling. Okay. And here I'm going to go into a little more detail about what I'm doing, in part because I think this section might be interesting, in particular to some of the conformal bootstrap people. It'll turn out that what we have to do here is basically just deriving conformal blocks. So this is just going to be a set of conformal blocks that are particularly useful for this very specific problem. Okay. So the idea is we start out by thinking of this using a melon representation. So in particular, we're going to assume that our solution has a form. Let's see. I'll start out writing this down here and add things to it as we go. So we've got some melon integral form. So an integral minus infinity to infinity, d nu. And we're going to assume that the answer has a form that's got z to the I nu over 2, f labeled by nu of x and y. So we've used this to diagonalize the dependence on z. So you can plug this integrand in now as an attempt at solving this equation. And what you get, and I guess I can actually just write this over here, since this has room for it, is a simpler form of this equation. So you just plug that in, and what you get is 1 minus y dy squared plus a quarter 1 minus y nu squared minus y g squared, all acting on f of nu x y equals 0. And once again, you also have the x exchange with y version of this equation. And this should maybe start to look a little more familiar because these kinds of equations, well, like many differential equations in the world, have hypergeometric answers. So in particular, since this only acts on y, you can propose a factorized form for the answer. So there's some, so your solution is now going to be some objects of the form f. Let's see, I'm going to write this a little differently. I'm going to use this plus or minus new index here. I'll explain what I mean by that in just a moment. But what we've got now are some product of a term that only depends on x and a term that only depends on y. And where the objects in here are defined as follows. So we have this j of nu, which contributes, is I root nu squared plus 4g squared. And then you can, perhaps more interestingly, this f of nu and j of, let's say, y is, we've got a hypergeometric, or we've got out front y to the I nu over 2, and a hypergeometric of, where the indices now, we've got I nu plus j over 2, I nu minus j over 2, 1 plus I nu, and then y as the argument. And out in front, we've got some normalization factors. There's some gammas, and basically all that they're doing is making sure. Did I write down what they're making sure of? I think the point is just to make f of 1 equal to 1. But anyway, these guys. Plus minus j over 2. And again, these are just to be specific, but the action is essentially in this part. Below, there's a gamma of, I believe, 1 plus I nu. Yes. Okay. So we have functions of this form. So this hypergeometric is what solves this differential equation. Okay. And once again, these should be reminiscent of conformal blocks that you run into in other contexts. Nothing yet, sorry. It was accidentally revealed because I had to go to this board. It will play a role in a moment, but not quite yet. Okay. But yes, and this ended up. Mm-hmm. Right, yeah. Mm-hmm. Okay. So from this point, you can start imposing some conditions this thing needs to satisfy. So one statement, which I'm not going to be able to justify here because I haven't fully described what x and y actually are, is that we want smoothness in small x and y. And that condition, in particular, means that we can have things that go like x, y in this limit, but we cannot have things that go like x over y in this limit, because that's ambiguous as x and y both approach 0. So what that ends up imposing is that, in fact, out of these plus or minus combinations, we really just have two options. We can have plus plus, just put this here, or we can have minus minus. Mhm. Yeah, that's trickier to explain without properly defining x and y, which I kind of was hazy about. But essentially, if you map x and y back to the actual momentum that's contributing to them, you find that indeed small x and y corresponds to a smooth region of momentum space where nothing interesting should be happening. And similarly, I'm going to make this statement, which again is not really justified in the context of this talk. Mhm. Mhm. They're not exactly those. They can be related to those. If it's informative, I can actually dig up the specific definitions in terms of them. But yeah, maybe later. But yeah, the statement actually is that x and y going to 0, if I'm remembering right, corresponds to uv and w going to 1, or to some combination of them going to 1. And that should be a smooth point. That isn't a special kinematic point. At least not unless something else is going to 0, but not by itself. Okay. And similarly, that same sort of reasoning can give you that this thing also has to be smooth when 1 minus x and 1 minus y switch signs together. So to be a little more specific, what I mean by that, what I mean is that when x and y cross 1, if they cross it independently, you can maybe get some non-smoothness, but if they're crossing it together, if you translate it back to the original kinematics, then you can see that there should be some smoothness when either they're both less than 1 or they're both greater than 1. And what this ends up imposing is that these things actually need to combine in a specific combination. So in particular, you have to have logs of 1 minus x times 1 minus y. You can't have them appearing separately in this limit. And what this does is this fixes the coefficient between these two terms. So it just tells you this has to be a negative. It has to be minus. Now, let's see. There's, yes. But there is one element I've left out of here, which I should have made more space for, which is that in principle, you can still have some arbitrary function of nu here. So some c of nu can show up here. We've trivialized the dependence on everything else, but we technically don't know what this is yet. So the differential equation doesn't fix this. The assumption that we're diagonalizing z with this melon rep doesn't fix this, so we still need some condition to fix this. Oh, and sorry, this is a function of g squared as well. But, okay, so step 1, let's see. Yes. So step 1, just kind of for convenience, one statement I can make about this C is that it should have maximum single poles. You can get logs when you perturbatively expand this, but you shouldn't get singularities that are worse than logarithmic when you perturbatively expand this, so you shouldn't get double poles. And what this ends up meaning is that it's convenient as sort of an ansatz to write C with, should remember this is a sinh, yes, sinh pi nu in the denominator. So this is just saying this can be any pole you like. Okay. Or they do have a log squared, but you won't get a log squared from a double pole. I think if you have a double pole and you're perturbatively expanding it, you get a single pole. So these things are going to be polylogarithms when you expand it. They're not going to be rational functions. So yeah, You can get a log squared, but don't think that would, a double pole would not give you a log squared. Unless I'm thinking about this wrong, but yeah, no. Let's see. Anyway, so, but yes, so then from this perspective, C is now some entire function. And to fix C, we end up using a boundary condition for large nu. So as it turns out, the part of this integral for large nu contributes to a particular region in kinematic space, and what it gives you is a region that grows linearly in the kinematics. Now once again, we can have only logarithmic singularities at loop level. So any loop level contribution to this thing cannot grow linearly in kinematic variables. And as a result, C can actually only contribute at tree level. So if C appeared at any higher loop order, then you'd get pieces in this large kinematic limit that contributed linearly at loop level, and that's not allowed. And what ends up happening is that C is just 1 over 2i. So I'll put the 2i down here. This is still looking messy, but that is what the answer ends up being. Right, so the idea is, so this is this boundary condition argument, which again, I'm perhaps not giving as much detail as I could, but essentially what this is this controls a limit for large kinematics. And in particular, it corresponds a limit where things diverge linearly in kinematics. Once again, I'm being a little hazy about this. I can show you sort of the step-by-step thing. I felt like it was a little too technical to go into in the talk, but basically, if you work through it, what you see is that if this thing did have higher loop pieces, then it would have to give rise to linear scaling kinematics at higher loop order, not just at tree level. So that's in principle possible. I think that, let's see. Trying to think what's the problem with that sort of behavior. Right, yeah. Right, yeah. So now in this expression, the coupling constant dependence is only in this J. So this J then imports the dependence to this F, which in turn brings it into the full expression. But there's no coupling dependence in the coefficient, it's just in the form of that. Okay. Let's see. So maybe I can kind of want to leave up both of those. Maybe I'll switch this thing. Okay, so that gives us an expression for omega. And I'm not going to go through it, but you can use a similar derivation. Where did that went here? Okay. You can use a similar derivation to get omega tilde. Okay, so that's two functions which now are defined for finite coupling. Okay. But more generally, we're sort of interested in building some space of functions. So let me start talking about what I'm going to refer to as the omega space. Okay. So I mentioned we have this omega tilde. Omega tilde, while it's a similar derivation, now involves derivatives of these f functions. So it'll have some objects like d dx f j nu of x showing up in its expression. But it's also going to be of weight 2 times the loop order. One can also define, I'll put this here actually, one can also define 2 more functions, a function O, which is 1 over g squared x dx minus y dy omega. So this is now breaking this xy symmetry. And a function w defined by x dx plus y dy omega. And if the g squared here seems a little arbitrary, it's just because it makes normalization for certain things nicer later. But the upshot is these things, as you'll notice, there's one derivative here. So we had some functions of even weight. Now we have some functions of odd weight as well. So what I'm sort of edging towards here is a space of functions that's defined at every weight. But we'll start with just these 4. And these 4, each one of them has an expression like this. Each one of them you can write at finite coupling in some Mellin representation. Okay. And in particular, these things will all involve some combination of derivatives of these f's and just these f's by themselves. And remember, these things obey the second-order differential equation. So in fact, they form a complete basis. Everything that you can write in this kind of form using either f's or derivatives of f's that satisfy these smoothness conditions I've been imposing, everything like that is going to be included in some basis composed of these things. And I'm going to write this in terms of some vector. So this vector here is going to have this w, it's going to have this omega, it's going to have, and I'm now going to say omega tilde even. Omega tilde has both a parity even part and a parity odd part. I'm just selecting out the parity even part. The parity odd part turns out to be related to these other functions in a fairly simple way, but it just singling out this part makes the next thing a little simpler. And finally, the odd ladder. And what I'm going to do here is I'm going to look at their new integrand. So rather than looking at the full Fourier-Mellin thing, I'm going to just take just the integrand of it. And what it turns out is that these things all, when written in this nice vector form, obey a matrix differential equation. So d of vi is d mij of vj, where m is now this matrix up there. So this should explain what this thing was for. This is this derivative matrix, which in turn relates all of these integrals together. So using this, you can find differential equations that take you from any of these integrals to each other. I've got this c variable here, by the way. This is just a shorthand for 1 minus x times 1 minus y. Also, because you did ask about the UVWs, c has a very simple representation in terms of those. It's just, need to remember which one, w over uv. So this perhaps clarifies why when this thing is switching sign, you can get a singularity, but only if these are switching together. Otherwise, it corresponds to something which shouldn't, which doesn't actually correspond to one of these vanishing. Anyway, let's see. Okay, so this is already kind of a nice space of functions. We've got essentially two functions at each weight now, omega and omega tilde at even weights, and w and o at odd weights. But what I'm interested in is not just these functions. Let's see, where do I want to write this? So what we want is not just these guys. Let's see, is this maybe? This is still fine. Okay. What we want is all f superscript s. And what do I mean by that? Well, I can go back over here. So remember, at any given perturbative order, we've got functions of this kind of form where their derivatives include functions of one lower weight. Now, they've got these d logs here, yes. But in particular, what I want is all of the different functions that can appear with different d log coefficients. So not just what appears when I apply some differential operator, but all of these different pieces. Because these pieces are the kinds of things we apply when we're trying to bootstrap things perturbatively. So we have to build them up order by order when we're bootstrapping perturbatively. What I want is some definition of all of these things that contribute to the omega integrals. Part of the motivation there is I want to compare it to the full space that I get when I try to bootstrap the amplitude, and to see how much of the amplitude actually is just omega objects. So I can start looking at this, and let's see. Here I'm going to regrettably, once again, revert to being a little hazy, which I apologize for in advance. Once again, it's kind of a technical derivation. It didn't really feel appropriate to actually go through it all here. But what ends up happening is that there's a simplification when you take the C discontinuity. So when you take a discontinuity of any of these functions in this variable C, what you get is that your melon integral instead becomes a contour integral. Let's just okay. And so when you're looking at the C discontinuity, then you can pick off any given contribution to it by Taylor expanding, and by just looking at the Laurent series. So in particular, what I can think about here is some more general set of functions. So the discontinuity in C of now this integrand vector, I can express in terms of a double Taylor expansion. So I've got L equals 1 to infinity here for the loop, and I've got some index k, goes from 0 to infinity. I've got the loop counting, and I've arranged it into minus g squared, because this ends up being a little more natural. Things tend to flip sign as you go from loop to loop. And then I also want to expand in this melon variable, and once again I've normalized it in a particular way just because this is a convenient way to absorb things. And I'm going to define these v tilde ikl functions. So now we've got a much broader set of functions, and these are specifically contributing to the discontinuity here. And with these things, once again, this matrix still applies, but now this matrix is going to relate different orders in both G and nu in this Taylor expansion. So you can sort of count how many weights different powers of G and nu contribute. And what this thing will do is, like, if it goes here, it'll be contributing to a function with two higher I, or a function with more k if you have one of these, etc. So this matrix then relates all of these different things together, and in particular, it just tells you the d logs that contribute to each order. So when you're building these functions up, what you really have to do is, again, just like these g functions, you start with some seed, and then at each order, you add these letters, and you have some integration boundary conditions so that you know what you're integrating to. And you can build up the symbol of these functions, or you can build up the functions themselves, order by order. And this time, in a very manifest, clean way, where you don't have to do it heuristically, you can just see how it has to work out. And in particular, what you get are objects. So these v tilde ik of L are what are called single-valued harmonic polylogarithms. So these are G's with weight vectors 0 and 1, and with some single-valuedness condition. So in the original context, there was a z and z bar variable. Here, you can think of the z variable used in traditional versions of this as 1 minus x, and the z var variable as 1 minus y. But this is essentially just imposing that 1 minus x and 1 minus y need to appear together. They can't flip separately. This is precisely the smoothness condition I talked about earlier. And so you build these kind of functions, and this is a perfectly well understood basis of functions. Mathematicians know how to construct it to any order you care about. You don't sort of have to just do it by brute force. You just know what it has to be. Let's see. So I left that part out. But then once you have these, you can then undo the C discontinuity. So the idea here is that these things are contributing to the C discontinuity of some functions. But you can take a step back and ask, okay, what kinds of functions can they be? And it turns out there's pretty much unique things that they have to be. So in particular, yes, so in this framework, yeah, okay, sorry, I left this out, but indeed, with logs of z to some power. Yeah. So z in these only appears as logs. So that's, again, very simple. But yes, thank you for reminding me of that. Yeah. Now, when you undo the C discontinuity, things are not going to be as simple. Now you can have more complicated functions, and they're not just going to fall into this very well understood class. But what you can do is you can characterize them by their derivatives. And you can find unique things that have to obey this. So in particular, let's see. If you have a function with no C discontinuity, so functions where its C discontinuity equals 0, these turn out to be simple. They're logs, they're harmonic polylogarithms, so once again, those are the 0 and 1 in the weight vector guys. They're easy to characterize. We can characterize those, once again, to any order. So, and in particular, in this space, there's just two at each order. So for this problem, in this particular space, two functions that have no C discontinuity can contribute, and everything else can just be completed in a essentially unique way in terms of these functions, where the only non-uniqueness is you can in principle add some amount of these guys to any function in this space. But you can make some particular set of choices and then get some explicit description of all functions that appear in derivatives of these omega functions, all functions that appear in this polylogarithmic picture to any order. So this is not something we can do in the full amplitude space. In the full amplitude space, we really have to do things order by order, essentially brute force. Here, we've got these omegas to any order we like. So what ends up happening is that there are 2n minus function, plus 2n plus 1 functions at weight n. Okay. Mm-hmm. Mm-hmm. Sorry, you mean the functions without C discontinuity? No, so these aren't ambiguities in omega. So a unique set of these will contribute to the omegas. It's just a statement of how you're defining your basis. So one statement here is the omega space is invariant. The basis you use for the omega space might not be. Okay. But indeed, this gives us 2n plus 1 functions at any order n. And then you can ask, okay, what would you actually do with these things? The slightly depressing statement is that this is not nearly enough functions to actually describe the full amplitude. When you look at the functions that actually contribute to the full amplitude, they grow maybe a little sub-exponentially, close to exponentially at least. So this is not going to grow fast enough. No, so actually let's see. So in terms of these, yeah, this is still the right set of building blocks, I think, or is there something else that I'm missing? Because let's see, there's Z, the 1 minuses, the 1 pluses. Yeah, so no, so these are two separate statements. So the omegas actually do have, or the omega space does have, C does not. So the nice thing about the C discontinuity is it collapses onto a much simpler space. And that's what allows us to reconstruct the whole thing. But the statement here is not so much that you get more symbol letters and thus things grow faster. That would have just changed, I guess, the scaling. It's instead actually that you are just delineating a very specific slice of this space. And the slice doesn't grow as fast as the space. Now that said, it is a lot of the space at low orders. The first few orders, really all the non-trivial functions in the space are omega-like. And it only happens once you go to 3 loops or so, you start seeing things that aren't quite omega-like, and eventually they start becoming more common. Okay. It doesn't clearly correspond to the minimal surface. It has some properties that are at least... so we have looked at that limit. One thing that it does is there's this exponential suppression. So it behaves in sort of a minimal surfacey way. It's the same sort of behavior people have observed for ladder integrals before. But it's not sort of an identifiable piece of the minimal surface. But regardless, this sort of gets us thinking. So I guess, let's see. Rather than, yeah, maybe I'll write them here, actually. These are just sort of the final speculations at the end. So things that we're interested in at this point. So one question is, this is one particular subspace of this full space. Are there other subspaces? Are there other things we could characterize to any order? And we suspect that there should be. That there should be more families of integrals that obey some set of differential equations that you can build up to all orders. And by seeing how these scale, by seeing what the space of those guys is, we could actually start populating the full space. Okay. But yes. But more generally, the more objects that we know for finite coupling, the more idea we can have about what sort of things contribute to finite coupling. And in particular, this sort of resemblance to the conformal block story is encouraging, because it suggests, I mean, and granted, I get the impression this is quite difficult, that if there were some understanding of conformal blocks that are appropriate for the full 6-point amplitude, and I was kind of looking forward to talk later today, but apparently it was canceled, on multi-point conformal blocks. But yeah, I mean, this is sort of an interesting question, is maybe the right answer is just you find the right type of conformal blocks that make sense for the full amplitude. And then if you had those, you could constrain it in essentially this kind of way. Bring in as much data as possible, make sure things are smooth in all the right regions, and try to actually get the finite coupling n=4 super Yang-Mills amplitude. Because, you know, despite the content of this talk, I don't think that's that implausible. I think that there's enough sources of information that it should be possible to have some nice form of the full finite coupling scattering amplitude for n=4 in the planar limit. All right, and with that, I'll end the talk. Thank you.